Andreas Zeller. I'm the author of the Debugging book, and I'm here to present you a new chapter. So, today's work, in contrast to some of the other chapters, is actually all new. This is a piece of work, piece of research that has been conducted just the last year and has been published in a scientific conference only 4 months ago in September 2020. And I'm happy to present it to you today, including a full-fledged implementation of everything there is. Our work today is about generalizing failure circumstances. And I'll be happy again to give you a live demo of how this whole thing works. So let me just prepare things here and let me see whether I can actually get this to run. So let me share my screen so that you can actually see things. No, that's not the right button. So here we go, share screen, and here we go. Wonderful, wonderful. Okay, you should all be able to see my screen on top. This is again Jupyter Lab with the generalizing failure circumstances. Johannes, Konstantin, can you confirm? Do you see something?
Yes, yes.
Wonderful, wonderful. Great, great techniques are coming along. That's so much fun. Okay, and actually, let's see whether this works. Actually, now I have a tool that allows you to draw on the screen. Do you see these drawings too?
Yes.
Cool. Oh, wonderful. Okay, let's take them away. I'll get back to things in a moment. Okay, so in this chapter, we're talking about generalizing failure circumstances, and this is actually a super central problem in debugging. We're having a program such as, say, the well-known remove HTML markup, and this program, well, occasionally fails. We've seen this already. And the question is, what is the set of inputs for which this program fails? See, if you have one concrete input and you know it fails, it's actually not very difficult to come up with a bad fix that simply checks, well, if the input is bad, or if the input is this very concrete bad input, then we come up with a proper result. This is called overspecializing the fix, which is a bad thing. But how do we actually know for which inputs this whole thing actually fails? And this is what we're going to do here in today's lecture. So we already have been talking about programs that fail, and we're going to look again into our well-known remove HTML markup program, which is surprisingly versatile. This is one single bad program which we can use again and again and again to illustrate one debugging technique after another, which is actually something that comes as a surprise. I had not anticipated that from the very beginning. And again, well, we have this remove HTML input, and we can feed it a bad input, which happens to be foo, quote bar, foo. And if we feed this into a remove HTML markup, well, it doesn't do the right thing. It removes the quote, and it also does not remove the second closing tag in there. Okay, now we can actually catch this error by, as in the chapter on assertions, we can add an assertion that actually checks for the post condition. The post condition at least should be that the output should no longer contain any HTML tags. And if we do this, then our function properly fails. At least now we have a failure here. But the general question is, if we're looking at this bad input here, okay, so at this bad input, how can we generalize this bad input such that we know under which conditions the failure actually occurs? And if we know under which conditions the failure actually occurs, we may even be able to generate additional tests that reproduce the error in various forms, such that we can really be sure that after fixing the error, that we actually have fixed it properly. So how does this work and what does it do? The technique we're looking at is called DDset, which stands for a combination of delta debugging and sets, which is in a way delta debugging on sets. That is, we want to find out an abstraction in terms of a set that tells us under which condition the program fails. And what we do have is, I'll get right away to show you how this works. What we do have is a so-called DDset debugger. This is a debugging technique, just as the other ones we've seen before. And this one comes with a magic parameter, which happens to be a grammar, simple HTML grammar. And this grammar, we'll come to that in an instant, describes the structure of the input. And we can apply this. This works very much like delta debugging and the other debuggers we've seen before. So we, what am I doing here? With the DDset debugger, simple HTML. I already imported things before, so things should work fine. So again, we use this like delta debugging and other debuggers in a with clause, which means that we are invoking it with a function call that re-invokes the error, which we can do right away. And after we have done that, we can simply print out the debugger in order to get a diagnosis. And what is this diagnosis? This diagnosis is an abstraction of the original input that we've seen, of the failure-inducing input, into what we call an abstract failure-inducing input. And in this abstract failure-inducing input, parts of the concrete input have been replaced by placeholders. And these placeholders actually stand for sets of strings that can actually be inserted at this very point. And what we have here is as follows. So we're having this, having three parts in here. We are having this opening tag here. So this is the opening tag. And this opening tag is followed by a quote. And this quote is then followed by some plain text. And this plain text is then followed by a closing tag. This is already the full diagnosis that this debugger gives us. The error occurs whenever you have an opening HTML tag, and it's arbitrary, it can be any opening HTML tag, followed by a quote, followed by any plain text, followed by any closing HTML tag. So this pattern actually tells you that that the error, it hasn't anything to do with what is in the concrete HTML tag. It also has nothing to do with what is in the concrete plain text, because the failure occurs for any plain text. And it also tells you that the error has nothing to do with the closing HTML tag. All of these parts of our original bad input, as we have it up here, all of these parts can actually be abstracted away into any parts. The important thing is that there is a quote followed by some plain text. Now, this is very useful in two ways. We get a more general picture of the conditions under which the error occurs, which B, we also see, as with delta debugging, which parts are important, which one aren't. So the concrete inputs are more important than the other parts that are abstracted away, which can be anything, which tells us here everything depends on the quote being present. So the error has to contain, the input has to contain a double quote. That's it. This is what we have to look at. So it gives us a hint on where to look at. And finally, and this is fun too, we can re-instantiate those placeholders again towards more inputs. And there's actually a method provided by the debugger here, which is aptly called fuzz. If we invoke fuzz for fuzzing, that is the act of test case generation, then we actually get more inputs that actually also are set to produce the error. These are inputs which actually are these are not concrete inputs, which are abstract, which are instantiations of our um, abstract pattern. So let us take a look here. What we have here, for instance, this is fun. So what we have here is we again have an opening tag, which is this Q0 something here, okay? And we also have a closing tag, which happens to be this, /n. And in between, we have an instantiation, which is quote 2. This is an input which we can actually take and feed directly into our function, our remove HTML markup function. So let's actually do that. So we take remove HTML markup and we feed in this input that is without quotes, and it fails again. Wow, that's great to see that this fails too. And even better than that, we can create an arbitrary number of such instantiations. So let's do, well, why not? Let's make another 20 or so. Here we go, range 20, blah. And we print this out right away. DD fuzz, there we go, and boom. And we get another set of calls, all of which are set to cause the failure again, because all of these are instantiations from our abstract pattern that we have seen up here. So again, what we see here is, well, let's take a look at this one, for instance. Here's an opening tag, and here we have a single quote. Here we have a double quote, and then we have a closing tag. And here we have an opening tag, which comes actually with a number of attributes. But then again, the text that is between those quotes, those tags, has a double quote, and here we have a closing tag, and so on. And well, if we fix the bug, then all of these inputs, all of these concrete inputs, should no longer fail. All of these should pass. Now, this looks pretty helpful, definitely, and it is pretty helpful too. It's also pretty precise, and that's the fun part. But how does this miracle machine actually do this? We can get an idea on how this works by looking into this ingredient that we put in here, which is a grammar, simple HTML grammar. This is a grammar, and I assume you've seen grammars in CS 101. This is a specification of the individual elements of the input. We can actually take a look into what how simple HTML grammar is defined. We go into the actual chapter and look up the definition of simple HTML grammar. So let's do this right away. Here we go. And if you ever looked into grammars yourself, you know that a grammar which describes the structure of an input consists of a number of symbols, each of which can get expanded into more symbols. And these symbols can either be concrete, that is terminal symbols, or they can be abstract, which is non-terminal symbols, and non-terminal symbols tend to be further expanded. Here is the start of our HTML grammar, and we see so we have a start symbol. This is what every input starts with. So we see that in the input being described here is HTML. And HTML, you see this is the structure of an HTML. And this, what we see here is a list, and these lists indicate alternatives. So we either have a plain text or we have a tagged text. Okay, so far so good. What is a plain text? And here we go into classic grammar definition. A plain text is either an empty string or it is some plain character followed by more plain text. And this is a recursive definition. This is classic for grammars. What is a plain character? A plain character is either a letter or a digit or other or white space. And each of these is defined as a list over multiple individual non-terminals. A letter is, well, some ASCII letter. A digit is a digit. Other is any punctuation except for opening and closing angles. Because if we would produce these as well, then the plain text would no longer be plain text. And finally, we have white space there too, which can be whatever. New lines, spaces, character turns, vertical tabs, horizontal tabs. I'm not sure. Are there any kind of reverse tabs or something? There's a couple of things in here. Vertical tabs. Who has ever used a vertical tab? I think it's \V or something. Oh, the old times when things were printed out on printers. So this was a plain text. This is standard definitions. And here we go into tagged text, which is actually more interesting. A tagged text consists of an opening tag, followed by another HTML element. Again, we have recursion in here, followed by a closing tag. What is such an opening tag? An opening tag is a less than character, that is an opening angle, followed by some identifier, followed by a greater than sign. And you see that we have to define these separately in here. So less than is less than character, because incidentally, our grammar definition uses the same less than and greater than symbols to actually indicate non-terminals. And which is why we have to express the presence of angle brackets by using special non-terminals, which is a bit cumbersome, but well, it's not too complicated. So an opening tag is either an ID enclosed in angle brackets or is an ID followed by attributes. And an ID is, not very surprising, a single letter, or an ID followed by a letter, or an ID followed by a digit. Note, an ID cannot begin with a digit as usual. A closing tag is actually the same as an opening tag, except that there is no attributes, and we have this less than / ID followed by a greater than sign, and we also have self-closing tags. If you look at HTML, this can be something like an image tag, for instance, which also has no closing tag because everything is already in the tag itself. And then we have definitions for attributes and everything. We've gone through the grammar, and the interesting thing is that the abstractions and names that we have here in the grammar are actually also used in our diagnosis. So what we see here as opening tag or as closing tag, these are actually the same identifiers as we've seen them in the grammar, and actually they also represent the same inputs. So when we say opening tag in here, this actually refers to opening tag in the grammar. So this can actually be any opening tag as defined in the grammar, that is anything with an angle bracket, an ID, and a closing angle bracket, or an ID with attributes. So the interesting question is, how does our DDset debugger get from this concrete input, which we have up here, to this abstract input as we have it down here? Okay. The answer to that is, well, it uses the grammar. And it uses the grammar in two ways. And it uses the grammar in two ways. What it does is it turns the grammar into, using the grammar, it turns the input into something that we call a derivation tree, also known as parse tree, also known as syntax tree. All of these are different names for the same thing. And this derivation tree represents the structure of the input, but now by means of grammar elements. What we see here is an input that is generated from the grammar, and you see here how the individual parts of the input are actually being represented in a tree, and the tree at the same time tells us the derivation steps. So what you see here is start. Actually is an HTML part. HTML is a tagged text. The tagged text is a self-closing tag. The self-closing tag consists of a less than sign, which we don't see in here, It consists of an ID, and the ID consists of the characters R and 9 and 0. And we have a number of attributes in here too, which is a couple of letters, W and T, and which is identical to some plain text, which happens to be empty again. And we have a greater sign here at the very end. So we can use the grammar to produce inputs. And when we are producing inputs, what we're actually doing is we are producing trees according to the rules of the grammar. A start symbol becomes HTML, HTML becomes tag text, tag text becomes self-closing tags. And if we want to know what the input actually looks like, all we need to do is we traverse the tree, and in the leaves, what we find is the terminal symbols, and these can all be appended to each other, which we actually, which in this case actually is something that we have in the very beginning. This is the input that is actually represented by this very tree. So we have FQC90 in here. FQC90, here we are. Here is F, here is Q, here is C, here is 9, and here is 0. So simply by traversing the tree again from left to right and going through the individual parts, we can then find the individual letters down here as they are being produced. So this is what we can do. So from a grammar, we can produce inputs. This is what's helpful for testing. But we can also parse inputs. For instance, if we take our bad input, which we have seen before, and we parse it into a tree, this is the tree we get. So we have a start, HTML, tag text, and we do have an opening tag, which happens to be, well, that's not very surprising. This is actually opening angle bracket, FOO closing angle bracket. This is our opening HTML tag. And on the other side, we do have the closing HTML tag. Yeah, it's closing tag. So it's again a closing tag over here is slash. And we do have F, O, and O at the other end. So all of these things are here. So, and now this tree tells us how the algorithm works. What it actually does is it takes the tree from the concrete input, which now goes into, which now has, for instance, this opening tag, FOO, and angle brackets up here. So we're looking at opening tag. And then what it does, it removes the tree. So it cuts off this anti-tree, which is there in the concrete input. And then it goes and creates a new tree, and another new tree, and another new tree by expanding opening tag using the rules of the grammar. And each of these inputs is being tested. And if all of these inputs, all of these expansions of opening tags, if all of them also cause the failure to reoccur, then what you get is an abstraction, because what we've seen is that all expansions of opening tag cause the failure to occur again, and therefore we can abstract this concrete input into this tag, into this placeholder as we see it here. Same goes for the closing tag. So for the closing tag, again, what the algorithm does, it takes away all of these parts which are down below here. Then it goes and re-expands it again into new outputs and tests all of these. And if all of these also failed, then we know that our closing tag might be a good placeholder, a good abstraction for the concrete inputs that we have all seen to fail. And we can actually look how this works by turning on logging, and then you will be able to see the individual tests that are being conducted by the debugger. So no tests yet. Oh, sorry, only when you evaluate DD, that's when you see the tests. And yes, it conducts quite a number of tests here. And just to give you an idea what it does here, so it starts, so remember, the concrete failing input as an opening tag of foo. And the first thing it does is it tries to replace foo by a couple of other opening tags. This one, for instance. And this one passes. So sorry. Oh yeah, this is the entire string. This doesn't work. Okay, so first it actually tries to replace the entire input, and but as soon as it finds, then it finds out that the failure no longer occurs, so it has to go into smaller subtrees. And the first experiment we see here is this one. So you see here on the right side, it still keeps the old input as it was before, but now it replaces the foo tag with a new one, and another generated one, and a third generated one, and a fourth generated one, 5, 6, 7, 8, 9, 10. And all of these cause the failure to occur, which is why it learns that, well, whatever is in the first tag doesn't really matter, so I can abstract this into an opening tag. Next, it tries to abstract away the text between the two tags. No such chance. It generates a couple of alternatives, but all of these pass. So obviously, having a double quote between these two tags is relevant. Then it finds out that if I put in a first quote in here, followed by anything else, always causes the failure. Boom, we're done again. And then it finally abstracts the closing tag, coming up with a number of alternatives here, and all of these alternatives fail just as well. And this is how it finally gets to this very abstraction. Now you may ask, well, so how many times does it actually try this out? And the magic number here is 10. This is the magic number as set forth in one of the parameters of DDset debugger. And the question is, well, I tried coming up with 10 alternatives, and if all 10 alternatives fail, all alternatives fail, then we can assume there is an abstraction there. Is this actually true? No. Simply because, well, what we are testing here is a Turing-complete program. And what we're trying to come up with is an abstraction that actually is a grammar. And you can imagine that this grammar structure, as we have it in here, can not necessarily capture precisely all the conditions under which the program produces a failure. So this will, by construction, always be an approximation. It can, of course, be if you're lucky, it can, of course, be extremely precise and precisely catch things. In any case, however, it's going to be useful because it points to the concrete parts, because it points to the abstract parts that do not matter and the concrete parts that do matter. It's one thing. And as we have also seen, we can easily use this as a fuzzer again to produce more inputs that also cause the failure. Now, we can actually feed all of these, say this one, into a Python eval function. Here we go. Oh, sorry, I have to put this into strings. How do I put this into a string? Yeah, I have to put this into a string. So let's take this one, quote, oh, sorry, quote and quote. Hope that works. Assertion error, thank you so much. So you can take any of these and use these directly as a test case. And, well, why stop with 10 or 20 or whatever? I mean, why not 200 of these? Boom, there you go. And you get test cases like crazy. And only if your fix actually addresses all of these, then your fix will be perfect. Yeah, that of course is not only the magical word of automated debugging, it is also the magical word of fuzzing or test generation. We do have an entire book and an entire course on systematic test generation. And the book is called the fuzzing book, not very surprising. There's the fuzzing book and there's the debugging book. And this is one of the techniques that actually brings both of them together. The important part that actually puts these two together is the grammar, which we use to, is the grammar, which here we use as a parser to parse existing inputs and as a producer to produce new inputs. And this is how we can do all this. This is how we can generate all these extra inputs, validate our hypothesis, and come up with good abstractions on why the program fails. If you're looking into the fuzzing book, you will even find techniques that actually learn such grammars automatically from given inputs. I'm not sure whether it can do HTML. That's something to find out. That's something to try out. But this is also heavy subject of research. So this is all new work, which is actually surprising because grammars have been around for, wow, tell me, uh, uh, 60, 70 years, context-free grammars. The whole theory behind them has been around for long. It's actually surprising that a rather straightforward approach like this hasn't been discussed before. But there is lots of interest these days in fuzzing and test generation. There's plenty of papers in the area every year, and you know, you fuzz things, and then you have a concrete input, and then it finally breaks things. That's great, but the question always is, does this error occur under other circumstances too? And yes, and this very technique, which actually won a Best Paper Award at the ISTA conference in 2020, this approach um, this approach is the natural next step after finding some failure with fuzzing, or actually finding any failure, namely abstracting away what is irrelevant and having you point to those parts that matter. Okay, in the book, or in the notebook in particular, you will also find more examples. So of course, there's a big implementation and everything, which is fine. And I would like to thank very much my co-author Rahul Gopinath, who has implemented DDset for the first time, so that I was able to build on his implementation and simplify this a bit further. But you will also find other examples here. We have square root. We have the square root function, which you remember, square root. If we put in a negative number, it fails. Can we also abstract this? Not very difficult. What we need is a grammar for integers. If we have that, then we can again use our DDset debugger, and which will then use various combinations of positive and negative numbers as expressed by the grammar. And it will also very nicely abstract the failure condition into, well, the program fails whenever there's minus followed by a number. So it fails forever for whatever negative number. If you're thinking that this technique would always be perfect, however, no, it doesn't, because it can only express failures as in syntactic categories and in syntactic structures. If your error comes to be as a more of a semantic nature that is dependent on the actual interpretation of individual parts, then it won't be as effective. So here, and you will also find this in the later chapter, we are creating a grammar for the middle program. You remember the middle program takes 3 numbers, and the assumption is that it returns the middle of these numbers, neither the greatest nor the smallest, but the one that is neither the greatest nor the smallest. And we create a grammar that builds us 3 numbers, which is fine. So we can use this for testing and everything. However, when we're trying to abstract a failure-inducing input with a DDset, what we find is it returns the exact same string, because there is no way we can abstract this further. There is simply, well, the abstractions we do have is alternate numbers positive numbers, negative numbers, but there is no particular syntactic feature as with respect to these numbers that could explain why and when the program fails. So this is where a technique like DDset will no longer be able to capture failure circumstances. Where it works best is when you have syntactic, when we have an input that has a couple of syntactic properties that can be broken down into individual parts, and some of these parts matter, other of these parts do not. By the way, if you have a grammar that describes some bigger configurations, for instance, and you want to find out under which particular, whether there's a particular, under which configurations this error happens, and under which, in which configurations the error does not occur, then you can also apply DDset debugger to find that out. Because if you have a multitude of individual numbers, strings, whatsoever, and all of these are independent from each other, then it's no problem for a tool like DDset to actually find out which ones can be abstracted away, which ones actually need to have the concrete value as seen in the concrete failing test. This actually could also be a nice project for you to try out at home.